So, hi everyone, welcome to today's session on linear algebra through geometry. I'm Rupesh Kumar, and today is Saturday, is 2 August 2025, and this session will be held from 6 to 8 p.m. So, this is a cover up session for yesterday's session, which I missed due to some personal emergency. Apologies for that. So, let's wait for a few minutes and then we shall start this session. Mm. So yeah, everyone, let's start the session. So I believe no one has joined the session yet. So what I will do is I will assume that you guys are here and I will be answering the questions, right? And if you have any doubts, you can always reach out to me in the next session. So I hope every one of you get to look at the pre-recorded video that I'll be sharing on YouTube, and then yeah, yeah, we can start from there, right? Slide. Let's start. So I hope my screen is visible and I'm audible. So these are the problems that we will be looking at in today's session. Fine. So let's start. So let's start with the first problem, which says, with respect to the following reduced row echelon form of the matrix A, which of the following is a valid conclusion? Fine, everyone. So I'm just testing if I'm audible, right? Yeah, it seems I'm audible. So fine, right. So let's start. So with respect to the following reduced row echelon form of the matrix A, which of the following is a valid conclusion? So I hope every one of you remember the reduced row echelon form for given matrices. So uh, so what do we mean by this row echelon form? So yeah, let me explain the idea. So basically, so yeah, row echelon form is basically says that the matrix should have following property. Basically, the for each row, the leading non-zero entry should be 1. So let's say we have a 3 cross 3 matrix and we have these 3 rows and columns. So let's take a 4 cross 4 matrix. Fine. So let's say this is a 4 cross 4 matrix. The idea is the leading non-zero entry should be 1, which are essentially the pivots. And then all other entries in the matrix for that particular column should be 0. So let's say if you have a 1 in the first row at first row, first column, then all the entries in the first column should be 0, like this. Now again, let's let's say we have some other entries which are filling up this matrix, which are non-zero, obviously, right? Which can or cannot be non-zero. Then let's move on to the second entry, right? So now let's say our second entry looks like this. The first non-zero element is this, and then we have some value here. So underscores mean there are some values here, right? So yeah, someone joined. So Vaishnavi, am I audible? Can you confirm by typing in the chat box? So Vaishnavi, if you are able to hear me, yeah, great, thanks. Okay, so if you have any doubts, please type in the chat box. At the instant you get one, right? So yeah, let me reiterate what I was starting with. So basically, we were solving the problems for week 2, and this is the first problem that I was looking into. The first problem says, with respect to the following reduced row echelon form of a matrix A, which one of the following is a valid conclusion, right? So for this, we need to understand what is the meaning of a row echelon form, right? What is the meaning of row echelon form for a given matrix? So So what is the meaning of a row echelon form for a given matrix? So basically, let's say I am right now what I'm doing, I'm explaining what is the properties of a row echelon form of a matrix. Basically, we form a row echelon form or echelon form of any matrix by using elementary matrix operations, which are essentially row swappings and row elementary row operations as well as elementary column operations. So whenever we are doing these operations, we always follow the same pattern. If you're following row operations, we do the row operations, right? So how to do is obtain these elementary matrices. You simply either swap rows, or what you can do, you can add a multiple of another row to a given row, right? These are the two operations that you can do in order to achieve these elementary row echelon form. And when you do these operations, the idea is which the matrix should look should have some sort of properties, and these are the properties that we are looking at into. So essentially, let's say we have a 4 cross 4 matrix which is in a reduced row echelon form. Then the property is the leading digit for each row should be 1. So the leading number for the each row should be 1, which is essentially known as the pivot element, right? So row, let's say we have this matrix and I'm writing up the row numbers and column numbers, and let's start from there. So I'm using the blue color to denote the row numbers. 0 1, oh sorry, yeah, row 1, row 2, row 3, row 4, and again column 1, column 2, column 3, column 4. So this is a 4 cross 4 matrix, right? Now we want to fill in the entries, but we know that it is it is in reduced row echelon form. This means the pivot element, the first element which is non-zero for each row should be 1, right? So for, let's say, row 1, the first element that is non-zero is 1 for column 1. Now row 2, we see that the first non-zero element stays in the column 3, row 2, which is element 1, and after that any value can be there. Again for row 3, uh, for row 3, the now since row 2 has 1 at column 3, then it must be ensured that all other entries in that column has to be 0. So row 1 entry column 3 has to be value 0, right? Again, other entries in the same column has to be 0. Now let's say for row 3, the reduced row echelon form, the leading non-zero number is at column 4, right? So you put 1 here, then you have to ensure that all other entries are 0 in that column. So this is the basic idea of reduced row echelon form. Fine. Fine. So this was something that we were looking into. Huh. Then if we know that the matrix is having these properties, then we can always say that we can always define some we can always figure out some properties of this matrix, right? So for example, if all the rows, the first property is if all rows have at least one non-zero entry, that means matrix is full rank and is invertible, right? Moreover, from the echelon forms, row echelon form, we already know that one general property, that number of pivot elements is equals to rank of the matrix. Fine. So, for example, for this example that I have taken, the rank is 3, right? By full rank we mean if you have a matrix by full rank, it means the number of rank of the matrix is equals to either number of rows or number of columns, whichever is smaller, right? Now let's figure out something from the given matrix we have here. So with respect to the following reduced row echelon form of the matrix A, which of the following is a valid conclusion, right? So let's say first option, it says the homogeneous. So let's look into this. So let's try to figure out something on our own, then let's look at the options, right? So what is the rank of matrix A? What is the rank of matrix A? Is basically number of pivot elements. We have 1, 2, 3. So the rank is 3, right? Then is it so number of columns? Number of columns is 4. Number of rows equals to 4, right? So from this, what can we say? Is it full rank? No, not a full rank matrix, right? It is not a full rank matrix because number of pivots not equals to minimum of rows, comma, columns, right? So this is not a full rank matrix. Now, if a matrix is not a full rank matrix, so what can we say about the solution of AX equals to B? Vaishnavi, can you tell me? If a matrix is not a full rank matrix, can you say anything about this property? So I guess we have one more student. So both of you, can you tell me something about the property from using the properties of matrices? Let's say we are saying we want to solve a system of equations whose coefficients of the variables are stored in the matrix A, and the variables are themselves are stored in vector B, AX, and the relation is AX equals to B. So what can we say about the solution of system of equations AX equals to B? Right? Anyone? If it's not a full rank matrix. So let me give you some example, right? So let's say we have these systems of equations. So we have a system of equation x plus y equals to 10. Very basic example, right? And then we have 2x plus 2y is equals to 20, right? So let's write this in matrix vector form so that we can try to solve the system of equations. So basically, how would you do this? You take out the coefficients in a matrix and call the matrix A. So coefficient of x in the first matrix is 1. First equation is 1. Coefficient of y in the first equation is 1 again. Then coefficient of x in equation 2 is 2, and coefficient of y in equation 2 is 2. Now this is the matrix A. Now we can define our matrix X, which contains the unknowns, which are X and Y, and we can write at the right hand side as 10, 20. Now we all know how to solve this system of equations. You can either use Gaussian elimination, right? Gaussian elimination, right? Or we can always do matrix inversion. If you are able to find matrix A inverse, then X equals to A inverse B, right? Or what you can do, you can form reduced row echelon form, which is essentially equivalent to doing Gaussian elimination, right? So let's try to figure out this. So let's use reduced row echelon form for this matrix. Okay, let me add a page here, right? Yeah. So let's do this, right? So the matrix that we are looking at is 1, 1, 2, 2, right? Into xy equals to 10, 20, right? So the easiest way, let's use elementary row operations to solve this using Gaussian elimination, right? So let's look at the matrix A, 1, 1, 2, 2, right? So let's do one thing. Let's perform some row operations. So let's say this is our row 1 and this is row 2, right? Let's replace our row 2 with row 2 minus 2 times row 1, right? And we get our matrix 1, 1 and 0, 0. Okay. Now this is a 2 cross 2 matrix. Now again, can we do any other row operations? No, right? We know this. Now, because we do not get any pivot element in this given row, right? All the entries in row 2, all the entries in row 2 are 0. So you do not have any pivot element in this entry. So you cannot do any other row operations for this set of matrix. Now this is in the reduced row echelon form. Now, how many pivot elements are there? Pivot elements, how many? We have only one. So what is the number of minimum of number of rows, comma, columns of this matrix is 2. So we can already say number of pivot elements not equals to minimum of rows or columns. Therefore, our matrix is not full rank. That implies pivot number of pivot elements 1 is not equals to 2, right? Number of Since number of pivot elements is not equals to um whatever, right? Min of number of rows, columns. So our matrix is singular, right? It's not a full rank matrix. It is a singular matrix, right? So A inverse is not defined, right? Determinant of A is 0, right? You can always verify this if determinant is 0. Let's try to find the determinant of matrix A. So determinant of A would be 1 into 2 minus 1 into 2, right? This is the formula that we know, 1 into 2 minus 1 into 2, which is equals to 0. So this means it's not invertible, right? Again, let's try to, so we don't get us, we have infinite many solutions, right? We have infinite many possible values of x and y that satisfy this equations, these two sets of equations, right? So let's try to solve this using Gaussian elimination, right? So it says x plus y equals to 10, 2x plus 2y equals to 20. And whenever you try to solve this, you won't get, because whenever you multiply 2 or do something, you get 0 plus 0 equals to 0, right? And any value of x and y will satisfy this. Any value of x and y. What does this mean? I mean, not any, but there can be multiple. So let me correct myself. There can be multiple values of x and y that will satisfy these two equations, right? Let's look it through the lens of geometry, like what it looks like, right? So again, like the usual examples, whenever we try to solve a system of equations, what we do, you plot them in the Cartesian plane. So we have the variables x and y which are unknown, and let's plot our equations. Our equations says x plus y equals to 10. So put x 0, then y will be 10. Put y 0, x will be 10, right? This line falls through this, and you can always draw a line passing through these 2 points. Let me try to draw a line, right? Mm. So this line would look like this, fine. Ah. So this is our first line. So this is our first line, right? This is the point 10. Let's try to plot our second point, right? So if x, again, the second line says, let me take the red color as the second line, and let me plot a dotted line, right? For second equation. So it says 2x, oh, sorry. It says, so let's say this is the first line that says x plus y equals to 10. And let's go on to our second line, which says, try to plot our second line, which says 2x plus 2y equals to 20. So this means x equals, when x is equals to 10, y equals to 10. When x equals to 20, no, x equals to, sorry, I made a mistake here, sorry. When x equals to 0, y equals to 10. Again, when y equals to 0, x equals to 10, right? So again, this passes through these two lines, these 2 points, right? X and y, 0, 0, right? Let me draw up this dotted line. So again, when you observe this, what is happening? Both lines are collinear, right? So basically, both lines lie on each other. They are basically parallel, and they coincide. So they are coinciding, right? These two lines are coinciding with each other. So the dotted line is represented by the red color, which is 2x plus 2y equals to 20, right? Both lines lie on each other. So there is no one single solution that satisfies both equations. There are multiple values of x and y that satisfy these equations, and those values are, so the solution to this equation is, solution is x equals to 10 minus y, right? Now you put as many possible values of y, you will get as many possible values of x that satisfy this system of equations. So there are infinite many solutions for these systems of equations. Fine, everyone? Right. So this is the idea of these points, right? So again, we saw that if you try to use some row transformations, elementary row transformations to form the elementary matrix, right? Echelon form, you will get that this is a singular matrix, so you can't invert it and you don't get any solution, right? Then if you try to solve this geometrically, you see that both lines coincide, so there are infinite many solutions. So infinite many solutions, right? So yeah, from the reduced row echelon form of a matrix, we can always find the number of pivot elements and compare with the minimum of rows and columns. And if it is a square matrix, it should be equal to a number of rows and number of columns. And if it's not, then the matrix is non-invertible. You will get infinite many solutions. The matrix will be singular. So let's look at now. Let's go back to our options that we have. It says so number of pivot elements we have 3. Number of rows and number of columns are 4. So this is not a full rank matrix, right? 3 is less than 4. So the homogeneous system of equations Ax equals to 0 as unique solution. No, it's not possible. Why? Because you have basically, let's say you want to say Ax equals to 0, right? So let's think of it like this. You want to find values of x that will give that will say ix equals to 0. So let's look at this. Let's say I am choosing my x. I'm giving a counter example. I'm proving that this is an invalid conclusion by giving a counter example. Let's say you take x is equals to some value 0 0 0 a, where a belongs to set of real numbers, right? A can be any real number, right? And let's do matrix product, right? Let me create some space here, right? So let me create some space here. Hmm, 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 right. Hmm, hmm, right. So let's try to do this matrix vector product, right? 1 0 0 0 0 1 0 0 0 0 1 9 0 0 0 0, and let's multiply it with the vector 0 0 0 a, right? When you will do this, when you multiply this, do this matrix vector product, what you will get. So now you are familiar with the way we look at matrix vector product, right? You will see that it will give you the value this multiplied by this, which is 0, this dot this, second row dot column, this vector, which is again 0, third row dot this vector, right? Hmm. Hmm. So it will give you 9a, right? And the fourth will give you 0. Hmm. Okay, this is not good. This is not good. So let's take some another counter example, right? For this example, you can see this only satisfies when a equals to 0, but I am sure that I can come up with another example also. So let's take this example, right? Uh, let's put it 0, 0, minus 9 and 1. Let's take this, right? Minus 9a, comma a. Let's take this, right? Huh. Let's take this for all a belongs to real number, right? So this is a for all operator that says that for all values of a that can belong to a real number, which is infinite values of a, right? You can always do this matrix vector product, and you can figure out this what will be this value. So now this value will become this 0, 0, minus 9a, comma a, right? Now this dot this will be 0, this dot this will be 0, this dot this will be minus 9a plus 9a, right? Which is equals to 0. And the last dot this will be again 0. So this is a 0 matrix. Now for all possible values of a in set of real numbers, so there are infinite values of x that satisfy ax equals to 0, right? So it does not have a unique solution. So this is wrong. Matrix A is invertible. Again, wrong. We already saw that this is not invertible because number of rank of matrix is 3, which is not the full rank. Rank of matrix is A is 3. This is true, right? We already saw this. And Ax equals to B has unique solution for every B. This is also wrong, right? Let's a simple counter example. Put b equals to 0 vector, then you will see that they are infinite values of x that satisfies this. So option D is also incorrect, right? Now I saw that Satinder had raised their hand. So do you have any doubt, Satinder? Can you I ask your question here? Is this what was the doubt you had? Satinder, am I audible? Any one of you please confirm if I'm audible, and then I would Satinder is typing. Yeah. Yeah, you can type in the chat box. Right now I okay. Satinder, can you just type in the chat box whatever query you have right now? So you wanted to speak something, you can ask by typing the chat box. It's very difficult for me to. So let me just enable the mic for you just for a while, then I will disable it. Right. Satinder, now you unmute and speak. Satinder, now you can speak. Uh, Please unmute and speak. Right. You can unmute and speak now. Can you try again? I just gave you permissions. Yeah.
Hello, sir. Excuse me.
Huh.
Thank you, sir. Sir, just I was telling what the previous example you took, no? So
Hmm.
since I what I found ki this comes out to be non-zero. So in that situation, it must have no solution then. If what the previously have taken that just now so it is coming 0 0 something like this. But before
Hmm.
what we took, so that was coming as a non-zero this side something because rank is less than uh, this rank is not equal to the matrix, so it must have the two options, I think so. Either no solution or infinite many solution, because both the situations can arise.
Yeah, let me think. If the rank of a matrix is not if a matrix is not full rank,
Yes,
then
sir.
basically what happens if you try to solve the homogeneous system of equation, right? For homogeneous systems of equations, you will always have infinite many solutions, right?
Always. So
Yeah.
situation can be that no solution also, no, sir. Because you took that example. Suppose x plus y equal to 10. If I'm going
Hmm.
to take
Hmm.
another example as 2x plus 2y is equal to suppose uh, uh, 15. So in that situation, so still we will get the rank less than zero.
Right.
So
But
no
that won't
solution.
be a homogeneous system of equation, right?
Homogeneous system of equation acha equal to नहीं homogeneous में so that comes out to be zero B matrix
Yeah, B vector has to be zero always if you are
always.
using if you are considering homogeneous
See,
systems of equations.
so homogeneous only two conditions are possible. And sir, one more I have the doubt. Sir, I have the problem
Hmm.
in reducing into like a Gaussian elimination method. It is always not working when we are solving the question. So sometimes we are get stuck into that. So while solving the questions by Gaussian elimination method, sometimes it is not
Hmm.
because of what I feel ki, last rows must be 0 0 x 3 something like that. So when it has no solution or something like that, so at that case it was not working. I think Gaussian elimination method and Euclidean method is still little bit. If you can explain, sir, please. RREF
Okay,
method
just
and Gaussian.
okay. Let me start once first. Let's start with the first doubt you had. So basically, you were
Yes.
saying that if a matrix is not full rank, then and if you are trying to solve a homogeneous systems of equation, so there is a possibility that there are no solutions, but that's not true. If
No,
the
not
matrix
not for
is
homogeneous. For
uh,
any matrix. For any
For
matrix.
any matrix, I agree with you. But
Not
if you are
homogeneous.
considering only homogeneous systems of equations, there can
Okay.
be multiple solutions that
Yes.
satisfy if the matrix is not a full
Uh,
rank, right? That is
yes,
clear,
sir.
right?
That is clear.
Fine. Now for the second problem, you are having some problems in solving Gaussian elimination, using
Yes,
solving
sir.
these systems of equations using Gaussian elimination, right?
Gaussian elimination and this one
So,
RREF form it is there, na? So that also
yeah.
the clarity is not there in that. What the concept of pivot and how to generate that part little bit. Although
So,
I have watched the
so
video, but still not confident enough
okay,
in that.
okay. So, yeah. Let me.
Thank you.
So can we solve a solution after I am done with all the
Yeah,
problems
yeah,
right now
yeah, yeah,
because
yes, sir, yes, yes,
there are other
oh,
students also and
yes, sir, yes,
I will
yes.
take up your
Thank.
questions during the
Okay, okay,
right.
okay, sir. Thank you. Okay, sir.
That's fine.
Sir, fine, sir. Thank you, sir.
Okay, okay, fine. So let me solve the problems and then we can come back to these. I will solve a few problems that will help you to get acquainted with these questions, right?
Okay, sir.
Okay, yeah, fine. So let's move on to the second problem. So Vaishnavi, I hope you have no doubts. And so proceeding with the second problem. You can also unmute and speak up if you want. I think okay. I think yeah, I should proceed with the second problem. Yeah, fine. So let A and B be 5 cross 5 matrices. Okay, fine. Let A and B be 5 cross 5 matrices with determinant of A. So whenever I am for my questions, whenever I am saying that yeah, whenever I'm saying some this mod box inside the mod box, I'm writing some matrix. This essentially means determinant of matrix A, right? So the question is, let A and B be 5 cross 5 matrices with determinant of A equals to 7 and determinant of B equals to -5. The determinant of the product B inverse is, right? So what is the determinant of A, which is equals to determinant of B inverse? Right? So I hope every one of you remembers the properties of determinant, right? So that will help us to solve the problem. So everyone, do you remember what are determinants? So essentially, determinant is the volume or a volume of the uh, pipe formed by the columns of the matrix, right? You all, I hope you all remember this, right? And we know one property of determinant, that determinant of AB is, let's take up the matrices as x, y. So determinant of x, y equals to determinant of x multiplied by determinant of y, right? Let's take this property and try to get the answer to this problem, right? So we want to find the determinant of B inverse, right? We can always say that this is equals to determinant of B into AB inverse, right? Now you can use this property. So use property 1 here, right? We can say determinant of B into AB inverse is equals to determinant of B multiplied by determinant of, oh, sorry, A into B inverse, right? It's no, A, oh, sorry. I made some mistake right here. Determinant of B into A into B inverse, right? This is B inverse, not AB inverse. That would have been something else, right? B into A into B inverse, right? So B into A into, right. Now we can always write this. So dot is basically a scalar product here, right? Now, now replace the value of, right, which is equals to, uh, yeah, implies, right. Now we know that determinant of B equals to, determinant of B is given, which is equals to -5, right? -5. So let's put it into this. So we get determinant of BAB inverse equals to -5 into determinant of AB inverse, right? Now again, use property, again, use property in equation 1 to solve this. So determinant of AB inverse is essentially determinant of A into determinant of B inverse, right? So now you are given a matrix B and you want to find the determinant of matrix B inverse. So everyone, do you remember the determinant formula? I hope you remember this. So we all know that determinant of matrix B is essentially, um, so if you remember, how can you say this? You can always write this. If you have a 2 by 2 matrix, or if you have a 5 by 5 matrix, right? And I want a relation between the determinant of matrix B inverse and the matrix B, right? So let's use the formula for forming the matrix inverse, right? Matrix inverse, and then we will try to find the determinant of the matrix inverse, right? So we know that B inverse equals to 1 by determinant of B inverse, right? Into adjugate matrix B, adjugate of matrix B, right? You all know this. Hmm. Now, what is now? Yeah, we can always say this. And then I want to find the determinant of. Sorry. Yeah. That's a mistake here. So determinant of B will be in the denominator here. Yeah. So 1 by determinant of B multiplied by adjugate of B, right? So now what I want to find? I want to find the determinant of B inverse, which is equals to determinant of 1 by determinant of B, right? Multiplied by determinant of adjugate of B, right? Right. Now, now what you know this.
Sir,
right?
excuse me. Can I tell something? Excuse me, sir.
Yeah, so you already know
Sir,
that the determinant you can yeah, so what I was getting to here is
sir,
basically you
sir,
know that this quantity will be 1, so this is basically equals to 1 by determinant of E. Yeah, what do you want to say, Satwin?
sir, I was saying ki directly we can use the property determinant of A inverse will be equal to determinant of 1 by A.
Sorry, determinant of A inverse will be equals to 1 by determinant of A, right?
1 by determinant of A. That one day I'm saying. This property
Yeah,
is also
that
here.
I was getting to this only. Yeah.
That you are proving
So
that part, I think. So,
yeah, I essentially show this. So
yes.
these are simple determinant properties and you get to this relation, right? Yeah. So now if you have this property, what you can see, you can always say determinant of AB inverse is equals to determinant of A into determinant of B inverse, which is equals to determinant of A divided by determinant of B, right? Now let's write in the values here. Determinant of A is 7 and B is -5, so equals to 7 by -5, right? Now I can replace this value in equation number 2, right? So using 2 and 3, we can say determinant of B into AB inverse is equals to what we got in equation 2. We say -5 into determinant of AB inverse, -5 into determinant of AB inverse. Now the determinant of AB inverse is 7 by -5, right? 7 by -5. So you get the answer 7, right? So option A is the correct answer. Fine, everyone. Do you have any doubts in this? I hope this is clear, right, everyone? So option A is the correct answer. So this is how you get to the answer for this problem. Do I need to explain anything else here? Satinder and Vaishnavi? I think Vaishnavi left the chat. Yeah. Vaishnavi, do you have any doubts? You can type in the chat box. Great. So let's move on to the next problem. So Vaishnavi, are you facing some technical difficulties? Is there some issue by my side? Okay, fine. I am not seeing any issues then. Yeah. So let A be a 4 cross 7 matrix with 4 pivot columns. Then let's try to answer this. So let's say we have a matrix A which has 4 rows and 7 columns, right? So 1, 2, 3, 4. 4 rows and 1, 2, 3, 4, 5, 6, and 7 columns, right? And we have 4 pivot columns. Then the system is inconsistent, system is consistent, right? Let's try to. Sometimes I'm not getting your audio. Okay. So Satinder, are you facing the same technical difficulty? Is my audio clear or it's breaking?
No, it's okay, sir. It's
It's
okay.
okay, right? So
It's
I believe Vaishnavi, there is some issue on your side, right? Fine. So yeah, let's look into the problem. So we have 4 pivot columns. The question says we have 4 pivot columns, right? Let's see how to solve this. So we have to, given this property, we have to say something about this matrix. So let's say by pivot columns, what we are meaning, we are saying we have one here, then we can have one in the so we have zero otherwise. Now in the second column, we can say 0, 1, 0, 0. The matrix looks something like this: 0, 1, 0, 0, 0, 0, 1, and some entries here, right? So these, let's say we are choosing these four as the pivot columns. This can be any other arrangement also. Basically, the column 2 can be swapped with column 6, 7, or any other arrangement is also possible. This is one possible case having four pivot columns. So let's try to say something about this. This first option says the system is inconsistent, right? So what do we mean by this? So let's say we are trying to solve the system of equations ax equals to b, right? Now, let's say if you have some x and you want to solve from ax equals to b. B is a given vector, then what you can say? By consistency, I hope everyone remembers the definition of consistency. Consistent system has at least one solution, right? At least one solution to ax equals to b, right, everyone? So I hope you remember this, at least one solution, right? So now we have four pivot columns. This means, so now again, what is the number of rows? This number of rows is 4. Number of columns is 7, right? What is the minimum of rows comma columns? Cos equals to 4, right? Now number of pivots equals to 4. So it's a full rank matrix, right? This is a full rank matrix, right? So the system is at least consistent. So the system is consistent, right? Consistent. So option one is wrong. It is a consistent system. Now we have to comment on whether it is having infinite many solutions or it has unique solution. So first thing is clarified that it is a consistent system, right? It is a consistent system that we are sure of, right? So the system is consistent. So any option that has consistent might be correct, right? So we do now what is the behavior? Does it have infinite many solution or it has only one unique solution? Let's look into this, right? So now for this we will have to look into the vector x, right? The vector x. Vector x will have dimensionality 7 cross 1, right? Hmm. So vector x has to be have 7 elements, right? Cross 1, right? Now, so this can look like something like this: 1, 2, 3, 4, 5, 6, 7, right? And b, when we talk about b will have the dimensionality r 4 cross 1, right? So this will look like symmetry 1, 2, 3, 4. So right. Huh. So whenever you take these dot products, right, you can have infinite many combinations of the vector x that will satisfy the solution ax equals to b, right? So you will get some infinite number of solutions. Why? Again, why this happens? So let me again take an example. So for example, I'm saying this option B is correct, right? Option B is correct. Option C is incorrect. You won't get any unique solution, and we have sufficient information to comment on this. How we can get to this? We can start by thinking of possible solutions to this, right? Uh, how to start with this? So let's say x is equals to x1, x2, x3, x4, x5, x6, x7, right? So now what would ax looks like? Ax is equals to, right? We can always say ax looks like x1 plus some summation of xi. I goes from 5 to 7, right? X2 plus summation goes to 5 to 7, xi, again x3 plus summation I equals to 5 to 7, xi, and x4 plus summation I equals to 5 to 7 xi, right? This is how our system would look like, right? The product x, and I want to equate to some vector b, right? For example, let me choose some vector 1 2 3 4, right? Then how many possible scenarios are there where you can get this solution to this problem, right? So you can always get uh, choose any particular combination of these x values to get to the matrix P here, right? Which is 4 cross 1 matrix, right? So we can choose x1 equals to 1 and all other xi's from 5 to 7 to be 0. So you can always choose this as 1, 2, 3, 4 and zeros char, right? You can always choose this possibility, or you can have some other possibilities where, let's say, right, these are non-zero entries, right? Some coefficients ci, right? So, right, this will be cixi, 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 right? So now you can now let's say if I choose x1 up to xn to 0, x1 x2 x3 x4 0, and I want to ensure that the other entries are 0, so you will see that you will get multiple possible values to ensure this, right? Multiple possible values of xi's to ensure that finally the sum is 1 2 3 and 4, right? So you can get infinite many solutions for this problem. Let me do this. Let me put x1 equals to 0, right? And x2 equals to 2, x3 3, no, x2 equals to 1, x2 equals to 2, x3 equals to 3, and x4 equals to 1, x5 equals to 1, right? 0 0. Again, you will get this. Again, you can reach p, right? You can again reach b using this combination for any possible values of c coefficients, right? So you will have infinite many solutions for this system again. So this is another solution that will satisfy this matrix system, right? Is this clear? Satinder, please explain your doubts.
Uh, so there is a little bit doubt ki if like matrix what we have,
Hmm.
so what I am able to see that it is underdetermined equation because
Okay.
number of
Yeah.
variables are more than that. So in underdetermined equation, does we have infinite many solution? And what is the condition for overdetermined? Matlab, like number of variable equations are more than the variables. That is
Yeah.
overdetermined, something like
Yeah.
that.
Yeah.
It
Yeah.
has
Yeah.
been explained in the tutorials. So there is a
So,
little bit confusion in that.
were the overdid is the overdetermined system of equations are covered? Are they covered? Like, do you know about least squares?
Not list squares, but I think little bit introduction has been given in the overdetermined or underdetermined equations, like number of equations that because we have given the assignments in that questions were also there. Okay, like
So,
number
yeah,
of
let me.
equations are number of variables are less than the number of equations, something like that it was, and
Okay.
that's why there was a confusion for this part little bit.
So let's start with the underdetermined case, and I will take a pretty basic example, very simple example. So let's
Yes,
say
yes.
we are considering a system in two dimensions, right? R2. Let's take the R2 space, and let's form some equation that I want to form. So let's say I am taking, so let's for consistency, let's take three systems of R3 system in three, and we are talking about inconsistent system, right? Sorry, underdetermined system of equations. So let our matrix be of dimensionality 3 cross 4, right? Right. So we have four variables and three equations. So let's put up this. So let's say x1 plus x2 plus x3 plus x4 equals to 1. Then let's say x1 plus 2x2 plus, okay, let me add, take it to a new page, right? Yeah, this will be really clear after this, right? So choose things, clear everything out, right? So let me take this here. Yeah, right. So what I was talking about, so I think R3 was getting too big. Let's talk about R2 only. So we could have, mm, right. So number of equations is less than the number of variables, right? We have three, then two, right? Yeah. So let's talk in R3 only. So we can have three variables and two equations, right? Three variables and two equations. Now let's formulate some examples, some system of equations, right? So let's say our variables are x, y, and z, and the relations are 2x1 plus 3x, oh, sorry, 2x plus 3y plus z equals to 1. And then we have very simple relation, x plus y plus z equals to 0, right? So we have two equations and three variables. Let's try to solve this. Three variables, two equations. Let's form the system of matrices. It will be 2, 3, 1, right? 1, 1, 1. And we don't have any more equations. X, Y, Z, right? Is equals to 1, 0. 4%. Yeah, fine. Right. This is our system of equations, which is underdetermined. We have less number of equations, right? Well, now what you want to do, you want to solve the system of equations. How you will do? In the 3D plane, what you do, you simply plot the coordinate axis, right? You can plot the coordinate axis in the 3D plane. So let's say we have this y-axis and then we have this x-axis, right? So this is x, now this is y. So in the equation says x plus y equals plus z equals to 0, right? So this is a plane that is at the that passes through the origin, right? So how can you write this? X equals to minus y plus z equals 0, then y equals to minus z. Okay, let's draw this plane. Put x equals to 0, right? So okay, you have a z plane also, right? So z will go out like this, right? In the 3D. Now, yeah, makes sense. X, Y, Z. Yeah. Now, if you set x equals to 0, you have y equals to minus z. So you have for x equals to 0, you have y equals to minus z, right? So in the yz plane, you have the relation mm, y equals to minus 0, which looks like what it looks like. It looks like y0, y1, so x minus, right? Y1 to Z minus 1. Yeah, you get something there, right? So it's like this, right? So Z, so you get this line. So you get this line in the YZ plane. Then again in the XY plane, you get this line when Z equals to 0, you get this line, right? And in XZ plane, you get this kind of line, right? Right? So now, how to look into this? How to look into this solution? So this is quite complicated, but let's make it simpler for visualization. How to understand the solution, right? Right. So let's choose x equals to 0 and try to find the number of solutions that we can get, right? Um, yeah. Yeah. So choose x equals to 0 and try to find some number of solutions. 3y plus z equals to 1, y plus z equals to 0, right? So you can now this is an equation in two variables and you can find a unique solution, right? Unique solution for this, unique solution, and it is defined. Now choose x equals to 1. Again, you will get 3y plus z equals to 0 and y plus z equals to minus 1, right? You can always solve these systems of equations, right? There are multiple solutions that exist for this combination. So essentially what I'm trying to do is I'm substituting the value of x, right? I'm substituting x with y plus z, right? So you can always write x equals to minus y minus z and put in equation 1, right? This is equation 1, this is equation 2. Put in equation 1, right? You can always say that 2 into x is minus y minus z plus 3y plus z equals to 1, right? 2 into minus y minus z. Uh, so now put this, so you get y minus z equals to 1, right? So this means y equals to z plus 1, right? So now for all z belongs to real numbers and y belongs to real numbers, right? So now this is a line, right? Y equals to z plus 1 is line, right? You choose this axis as y, this as z. So y equals to z plus 1, put z 0, y 1, put y 0, z minus 1, right? So this is this line. And there are infinite possible values that satisfies this relation. Yeah. So you have infinite solutions for this situation, right? So this is a quite complicated example, but yeah, you can always do. You substitute the value of x in terms of y and z, put in the previous equation, and you will get something like this. You will have infinite number of solutions if the matrix is full rank, right? Now, if it is overdetermined, then what does it mean, right? So is this clear? Is this case clear, Satinder? So this is
Yes, sir. Yes, sir. Yes, sir.
underdetermined, right? Right. So now take overdetermined, right? You are right that there will be no unique solution, no solution, right? In overdetermined, you can have situations like this: x plus y plus z equals to 0, 2x plus 3y plus z equals to 1, and then 5x plus y plus z equals to 2, and 6x plus 1y plus 3z equals to 3. You get this kind of situation, right? And you will never get a solution for this kind of system. No solution. Solution. So there is no single plane. There might be plane if one of the line is essentially scaled version of another, but there will be no solution generally, right? If A is full rank, right? If A is full rank, no solution. What is happening in this case? So let's say you have some dimensional, three-dimensional space in which you have multiple points, more than one point, right? So let's say you have these sets of points, one, two, three, 4, 5, which are not planar, right? So now you want to fit some plane into these set of points where let's say these 3 points, let's choose any of these 3 points which lie on this plane, right? We can choose 3 points that lie on the plane, but the other two does not. So you will always get this kind of situation where only 3 points will lie on the plane, the others will not, right? So these blue ones are on the plane, the black ones are not on the plane. So this is a overdetermined system of equation. You will never get a plane that will satisfy all the points. So yeah, in this we use something known as least square solutions that you will see in the future lectures, right? Use least squares here, but yeah, you won't get a solution. Fine, Satinder, is this clear?
Yes, sir. So what the question we have discussed just now. So we
Hmm.
can have a look in that key. It is a underdetermined equation. So it will be consistent and has infinite many solution. We can have that solution in that just now. What question you have solved, sir?
Ah, yeah, fine. Yes, that's true. And to ensure that it has infinite many solutions, you have to ensure that the matrix is full rank, right?
Yes, sir. So what the question we have discussed, that only what the example was given, that one,
Hmm.
just like 4 cross 7, in which it was uh, like one in the four column, like that is four pivot were there. So it is a
Hmm.
full rank matrix.
Hmm.
So we can say that it is underdetermined. So it has infinite many solutions, okay, consistent and infinite many solutions.
Yeah, right. Yeah,
Thank you, sir.
right. So I think Vaishnavi, do you have any doubt in this? I think no. Yeah. Let's move on to the question number 4, right? So suppose A is a 4 n cross n matrix whose all elements are either 0 or 1, the maximum number of zeros that A can have for it to be invertible, right? The basic problem. Right. A is n cross n matrix. Now, for A to be invertible, right? For A to be invertible, what is the property that we want? And A is a square matrix, then number of pivots in RREF is equals to number of rows, which is equals to number of columns, right? Right. So we need at least, at least how many rows with at least with p of pivot? We need at least n rows. So right, number of pivots, and again we know that number of pivots is equals to rank of matrix, right? And for it has to be invertible, rank should be full rank, right? It should be full rank, right? That means number of pivots should be, number of pivots should be equals to the rank of the matrix, and A is invertible, so it has to be full rank. And if it's full rank, the number of the rank of the matrix would be n, right? Are we clear on this? Is this clear, everyone? Do I need to explain why, how we come to this property? This is a very basic property, right? Ah, fine. So number of we want the number of pivots should be n, right? It should be n. Huh. So if we are saying that the number of pivots in n, how many entries are non-zero? How many entries? That implies how many ones? How many ones we should have? Ones we should have. We should have n ones, right? N ones. We should have, that implies n non-zero entries, right? Now, total entries, how many entries we have? Total entries we have n into n, which is n squared, and n has to be non-zero. So what is the maximum number of zero entries we could have? So the maximum number of entries with zeros will be equals to n square minus n. Right, everyone? Is this clear? It is a very straightforward problem, right? You have need to have at least n entries with ones, and others can be zero if you want to maximize the number of zeros. So what is the correct option here? Option n square minus n, which is option C, is correct, right? All others are wrong. Anyone, do you have any doubts on this? Satinder, Vaishnavi, do you have any doubts on this? Great. Vaishnavi, do you have any doubts? Please type, or we can move to the next question. Okay, I am believing that you have no doubts. So let's move on to the next question. Suppose A, B are two n cross n matrices with determinant of A equals to 2, determinant of B equals to 5. Then again, what is the determinant of A cube B inverse A transpose? I hope everyone, can you solve this? Now you can solve this, right? Let me give you some properties that will be helpful. So determinant of xy equals to determinant of x into determinant of y. This is the property 1, let's say. The second property we can say determinant of x inverse equals to 1 divided by determinant of x. Let's say this is property 2. Then again, determinant of x transpose is equals to determinant of x. This is property 3, right? Now you can use these three properties to solve this problem. And we need another property. Determinant of x raised to power n equals to determinant of x raised to the power of n. This is property 4, right? These are the four properties that will be useful and you can solve this problem. So let me quickly give the answer to this. The answer would be, let's start with the last part. Determinant of B inverse A transpose will be determinant of B inverse, which is 1 by determinant of B, which is 5, into A, which is 2, equals to 2 by 5, right? Now, determinant of A cube would be the determinant of A cube, which is 8. Oh, sorry, let me write this, equals to 2 raised to power 3, which is 8, right? Now we can always say determinant of A cube B inverse A transpose is the product of these, 8 into 2 by 5, which is 16 by 5. So option B is the right answer. Fine. If you have any doubts, you can ask me. Otherwise, I think we should proceed. Fine, everyone. So I think there are no doubts to this problem. Vaishnavi, should I explain this? You can always solve this if you proceed with the properties that I have explained here. So these are the four properties. These are the properties and use them to get to the answer. Right. Let's move on to the next question. Question number 6. Suppose a system of equation in the variables this leads to the row echelon form, which is this. Then the free variables are, right? Everyone, do you remember the class lectures? What are free variables? So non-zero, non-pivot variables are free variables, right? You remember this? Anyone, can you answer this problem for me? Okay, fine. Let me explain. Now, let me again write this matrix here in the form we want to see it. So we have 0, 1, 2, 3, 0, 0, 1, 0, 0, 0. And the augmented form is written here 4, 1, 0, right? So now the column 1, all the entries in column 1 correspond to the coefficient uh, x1, column 2 corresponds to the coefficient x2, column 3 corresponds to the coefficient x3, and column 4 corresponds to the coefficient x4, right? Now, now, what are the variables whose value will not change these systems of equations, right? Which variables won't change these systems of equations? So what is the coefficient of x1? All the coefficients that correspond to the x1 are 0. So x1 is a free variable, right? X1 is a free variable. Now x2, one of the coefficient corresponds to the pivot element. So it is not a free variable. X3 again has a pivot element, so it is again not a free variable, and x4 doesn't have any pivot element, so x4 is a free variable, right? So the correct answers are x2, x1, and x4, which is option C is correct, right? So let's think of what does this mean. By looking at the row echelon form, you know that if the coefficient of any of if of a variable in any of the rows is 1 is a pivot element, then it has to be non-free, right? Then what is the meaning of these free and non-free variables, right? Let's look into this. Just do the matrix vector product and you see what you will get. So let's do this: 0 1 2 3, 0 1 0 0 0 0 0 into x1, x2, x3, x4, right? This is essentially, right? This is essentially sorry, let me write this. This is equals to what we are expecting. We are expecting to get 410 on the right hand side, right? This implies, if you do the matrix filter product, it says 0 into x1 plus 1 into x2 plus 2 into x3 plus 3 into x4 is equals to 4. Now, 0 into x1 plus 0 into x2 plus 1 into x3 plus 0 into x4, sorry, 0 into x4 is equals to 1. Now 0 into x1 plus 0 into x2 plus 0 into x3 plus 0 into x4 equals to 0, right? So the last equation doesn't give us any information. It is essentially saying you take the 0 times all the variables, you get the value 0, right? Let's look into the top two rows that give us some information. Now let's observe the behavior when we change the value of x1. If you change x1, let's say you check x1 equals to 10. Does it change the RHS value? Will it change? Now we are multiplying it with 0, right? So x1 multiplied by 0 will always be 0, no matter what the value of x1 is, right? x1 multiplied by 0 will always be 0. So you can have infinite possible values of x1. So x1 can be any value in R1, right? Any value of in R1, it won't change the equation. So x1 is a free variable, right? It does not change the line which we are trying to represent through this equation, the plane, right? Now x2. X2 has a coefficient of 1, right? What does this mean? This means if you change the coefficient of x2, things will change. This plane will change, right? So x2 is an important variable, right? Again, when you look at x3, this is important. X3, again, x3 is multiplied by 1. So if you change x3, the equation changes, right? Right. Now look at x4. You may think that if you change x4, the equation's value will try to change because of x4 multiplied by 3 here, right? But what all we are trying to say this is x4 can be written as 4 minus x2 minus 2x3, right? And x3 can be written as 1 because all other coefficients are 0 in its row, right? That's it. That's all information that we are getting here. Now what I'm saying is x3 is not free. X3 is fixed to be 1. Again, x2 is not free because it contains some pivot here, and x3 is fixed. So x4 is free. X4 can have any value depending on the values of x2 and x3, right? X4 from equation 1, if you only look at row 1, x4 can have infinite values that depend on the values of x2 and x3. Now equation 2 essentially restricts x3 to be 1. So by equation 2 we can say x3 is fixed, x3 is not variable. But x4, if you consider equation 1, x4 is independent. X4 depends on x2 and x3 only. So x2 and x3 determine the values of x1, right? X4, right? So x4 is also free variable, right? Is this clear, everyone? So what I'm trying to say, yeah, Satinder, you can speak.
Sir, can we do in this way also? Can we visualize? Suppose if I'm going to insert 000 in the top column from my side,
Okay.
top row,
Hmm.
I'll if I'll take as 000,
Hmm.
so it comes out to be 4 cross 4. There will be no harm.
Okay,
It
fine.
is so what I'm saying ki pivot element in the first row is 0.
Uh, yes, fine.
So it means ki x1 is since it is the no one is there in the first row. So it means ki x1 is what free.
Yeah, right. Huh.
Fit, then I can see visualize that then in the second I am getting pivot as
Yeah.
1 means ki x2 is 1. So can we
Hmm.
visualize in this way also?
Yeah,
The
that also works. That
third
also
also
works.
I'm able to see 1, and fourth I'm not able to see any one pivot. So it will be again 0.
Hmm.
So x1 and x4 will be free. Can we so that only I had the doubt ki what is the concept of pivot and how to reduce into that. In the previously only I have asked that part only.
Okay, fine. So basically, the idea of pivots is like this. You are, whenever you do Gaussian elimination, you try to find some upper triangular form of the matrix, right? So what you do when you do a Gaussian elimination for any system of equations, what you do, let's say you have n number of variables, x1, x2, up to xn, right? What you want to do is eventually you want to get some equation, you substitute xn with some linear combination of x1 up to xn minus 1. Then you repeat this process. Now you replace minus 1 with some combination, right? And eventually you hope that you will get that x1 equals to some fixed value, right? So x1 equals to some a, right? A belongs to real numbers, right? Now you again keep putting the values of x1 in the equations eventually get xn. So the idea of pivots is that you are trying to find these values, right? You are trying to ensure that x1 in the last row, only x1 has some coefficient, right? Now if x1 has no coefficient, right, if the coefficient of x1 is 0, for example in this example we are getting coefficient of x1 as 0, so x1 won't change the equation, right? So the systems of equation is independent of x1. You are getting what I'm saying? So if you choose x1 to 100, 200, 1000, 10,000, it will never change the system of equations. It will never change the lines, whatever lines you are trying to find the intersection of the lines, it will never change that intersection point. Are you getting what I'm saying? If the coefficient of x1 is 0. Satinder, is it clear? You can speak up also. What? Right? And now, if you change x1 by any value, the system of equations won't change. That is the concept of pivots. If x1 had any of the variable had one of the pivot element as their coefficients, then they are responsible for changing the point of coincidence, right? So that is the main crux. So you need to have a fixed value of x2 and x3 in order to ensure that these systems of equations are satisfied. You can choose any value of x4, it will satisfy any value. If you can choose any value of x1, it will satisfy. That's the main idea. Fine. And if you want to look more easily into this, you can simply follow the basic idea of substitution. When you will do substitutions, you will see that the free variables can be represented in terms of non-free variables, the variables which are essentially associated with this entries, right? So you will observe that, for example, in this example also, you can say we get no equation of x1. X1 can be anything. X4 can be written in terms of x2 and x3, right? And then x2 and x3 has to have some fixed value in order to have fixed solution for this problem. You can't have any values of x2, any arbitrary value of x2, but any arbitrary value of x4, which is dependent on x2 and x3, and our x1 will work. So this is the concept of free variables. I hope I was able to make this clear, right? Vaishnavi, I will get back to question number 4 again. Question number 5, right? So Vaishnavi, I will ask you to solve question number 5, how can you solve this problem? You can use these four properties, matrix determinant properties, and just disintegrate this determinant problem into a set of problems, right? So first you solve for determinant of B inverse A transpose, then you solve for determinant of A cube, and then you can always say determinant of, use first property, determinant of A cube, which is a matrix, multiplied by matrix B inverse A transpose, right? Now this can be written as determinant of A cube multiplied by determinant of B inverse A transpose, and now put in the values. This is a simple problem, right, Vaishnavi? I hope you get the solution. Try to go back to the lecture and see the solutions, right? Satinder, is this clear?
Yes, sir, I've got it.
Yeah. So basically, free variables are the variables that can be represented in terms of other variables, and the non-free variables are essential for the solution of this equation, right? So let's move on to the next question. So given a non-singular n cross n matrix, the product A into adjugate of A is equals to, right? So for this, we will use the formula for inverse, right? The formula for matrix inverse. So we all know that A inverse equals to 1 by determinant of A multiplied by adjugate of A, right? Everyone, do you remember this formula? I hope so. Now what you want to solve, you want to find what is the value of adjugate of A. So adjugate of A is equals to determinant of A into A inverse, right? Now what is the value of A into adjugate of A? This is essentially determinant of A into A multiplied by A inverse. And we all know that A into A inverse is identity matrix, right? This is identity matrix. You would get A into identity matrix, right? So option C is correct. Right? Option C is correct. Is this clear, everyone? Do you have any doubts? Great. So let's move on to question number 8. You are told that a system of m linear equations in an unknowns has infinite many solutions, right? So you have m linear equations, right? And n unknowns. And it has infinite solutions, right? Then which of the following is true? Okay, let's look into this. Now we are saying we have some solution, right? So it has to be it can't be over determined, right? It has some solution, so it can't be over determined, right? It can't be over determined, so it has to be under determined or fully determined, right? Either it will be a square or rectangular matrix, right? And it has at least one solution, right? Has at least one solution, right? This means, what this means? This means that we have at least one pivot variable, right? So at least one variable is changing the systems of equations, changing the points of coincidence, right? So you have at least one solution, so it has at least pivot variables. And since it has infinite solutions, so it has to be one free variable. So it has to be have at least one free variable. So option A is correct, right? Is this clear, everyone? This is basic definitions of matrices, prompt definitions and properties of the matrix, right? Great. So let's move on to the next problem. You are told that rank of 5 cross 7 matrix is 2. Which of the following is true for system of equations, right? Fine. So you have a rank 2 matrices, right? A rank 2 matrix can be written always as, if you define the RREF of a matrix A, it will have two pivots, right? Which is equals to rank of matrix A. That we have already seen how we get to this. So let's say we define this matrix look to be like this: 1 0 7 0 1 0, 5 3 4 5, right? 1 2 3 4 5, right? Now other entries can be anything. These has to be 0, these has to be 0, these has to be 0. Now these entries can be anything, right? These entries can be anything, and this matrix will look like this, somewhat look like this, right? If not, you can always use column swaps to get to this, right? And yeah, you are to try, you are trying to solve x1, x2, x3, x4, x5, x6, x7 is equals to b. You want to try to solve this problem, right? So how many variables have pivots associated with it? Only two, right? So you have two pivot variables, because we can see we have only two pivot rows having only pivots are only two rows, right? So how many free variables we have? We have five free variables. So the correct answer is option D, I guess, right? Yeah, option D is the correct answer. So if you have this system, you will have five free variables and two pivot variables. Is this clear, everyone? This is again definition based. Great. Let's move on to the last question. Then I will explain a geometric interpretation of everything that we have done. That will hopefully help you guys to understand why we do this pivoting operations, right? You are told that the system of linear equations Ax equals to B has no free variables. Then which of is not a valid conclusion? Where? So we have no free variables, right? No free variables. What does this mean? This means A is invertible, right? A is full rank, right? So whenever you get free variables, this essentially means they can be represented in terms of other pivot variables. So if you have no free variables, then all the variables are important. So it is a full rank matrix. So every column has a pivot variable, right? So what is not a valid conclusion? A is a full matrix. It is true. So it's a valid conclusion. So pay attention to the question, what it says. It is asking for not a valid conclusion, right? Right? Yeah. So A is invertible. A is invertible. And Ax equals to 0 has only trivial solutions, right? Let me think. Yeah, that's also true, right? Hmm. Okay. Yeah, then, okay. Every column has to be a pivot variable. That's also true, right? Ax equals to 0 has only trivial solution. That's also true because there are no free variables, right? So if you want to say you are trying to solve the systems of equations, you will have to have at least you will have to allow for 0. All the elements has to be 0 if it has no free variables, right? Yeah. So let me think of this problem, right? X plus y equals to 1, 2x plus 2, right? So now this system of equations form this matrix 1 1 2 3, right? You do some operations to get the pivot form. You will, okay. Hmm. So yeah, I just want to think how it is not invertible, right? Okay. So if it has no free variables, then it has to be a square matrix, right? If it has to be no free variables, then with ones along the diagonal and other entries can be anything. So I'm not sure. Am I missing anything here? It has to be invertible, right, everyone?
Uh, Hello, sir.
Yeah.
If it will be 3 cross 3, if it is a plane, then maybe it is not possible, not invertible. If we'll go that only, I was facing the problem for the no, RREF form and what I have asked in the beginning, the Gaussian elimination method and RREF method formulation. We are facing little bit problem while converting because sometimes it is not coming, and there was a doubt that it will have a no solution or what. So that only I was facing the problem in between what I've asked in the beginning.
So which example? Can you set up an example for me?
That too, just we have to think it off. You have to frame.
So you are saying if it's a plane, right?
Hmm. So maybe that determinant comes out to be zero. It may happen. Two, we can see no solution is possible when the lines are parallel. So in that case, there will be no free variables. That is also not possible. I think so. Yeah.
Okay. So you are saying x plus y equals to 1 and 2x plus 2y
Equal to
equals
five,
to
something
2
five.
2 2 2.
Uh,
No, it won't
okay.
be 5, right?
This will be the coincident line.
Right. Okay, yeah, equals to 5. Let's choose this. Hmm. Okay, so they are two different. So yeah, let me make it simpler. X plus y equals to 5, right? So the first line goes like this. The second line goes like this, right? So you won't get any solution for this, but hmm,
Can we convert this matrix what we have just now 1 1 1 1 in that RREF form?
hmm.
And let's see this one.
You can't actually convert this into RREF form. I mean, you can always, right? You can say this R1 is R1 minus R2, right? Oh, sorry, R2 is R1, R2 minus R1. So you will get 0 0 XY to 1 5, right? You can always say this, right? So it's not a full rank matrix, so it's not invertible, right? And is this clear, Satinder? At least you can do this row operation, right? Am I missing
So
something here?
what the question has been asked here, no free variables, something like that it has been asked.
Yeah, that's what I'm trying to figure out. Like in this example, you have a free variable y, right?
Yes, sir.
You are having a free variable here. So I'm not sure about this problem, I guess. But my ideas are clear, right? The idea of pivot variable, it's simple, right?
Yes, sir. Yes, sir.
So I guess none of the options is not a valid conclusion. So let me quickly check
Yeah.
once, right? Let me just confirm if I have.
Like for plane, can we think like for the plane, can could it be possible like the two planes may be intersecting and the third is the Maybe in that case, it may be coming. It may come that the variable there are no free variables. Something. And
For
what is the meaning of the
planes.
free variables? That I'm not understanding. Like we can see here, first pivot is one. So
Hmm.
x is only the free variable,
Hmm.
but y is not free variable. We can see now because
No,
for the
X is the
second
pivot variable here, right?
pivot variable and y is free variable.
Hmm.
So there is so in this scenario it is written that no free variables are there. Something. So maybe
Yeah,
in three
I'm saying that,
dimension
whenever you are trying to set up,
for the
okay,
three
so you are
dimension it
saying
may come.
if the plane is a solution, right? We can think
Yes,
of
sir.
this. That will be equivalent to saying that x plus y equals to, let me write this. That will be equivalent of saying that x plus y equals to 1 and 2x plus 2y equals to 2. So that will give you equations 2, 2, right? Again, this is not a full rank matrix.
Hmm. If we take the example for underdetermined equation, something like that, maybe it may happen. But
Hmm.
for underdetermined, we won't get any determinant factor because in that
No, no.
case,
If you are solving, you are talking about underdetermined and it's saying it has no free variables, then how it's possible, right?
actually, that is not possible. Or overdetermined in that case also overdetermined to no solution will be there 100%.
Okay. Okay. Yeah, yeah. Okay. And let's not go into overdetermined case, but yeah, for underdetermined case only, we can say that we have a matrix like we have a solution like this, right? X1, X2, oh, sorry, some possible value of X, Y, and then 0, 0, 0, something like this. And we can have some system setup that gives me, that doesn't make sense. That doesn't make sense. Okay, let me just quickly check if the idea I'm thinking is wrong or right, right? So basically, I can't come up with a counter example. I'm looking on the internet, right? Let me check here. Oh,
Sir, can it be like option A will be wrong only?
what does it say? A is a full
Option A,
rank matrix. No,
which
basically, it
is not
can't
valid.
be. It has to be full rank, right? What is this? Yeah, this question like option A and option C.
Mm-hmm.
Okay, so if it's a full rank, hmm, and it has no free variables, right? Okay, now yeah, now I can think of some idea. So let's say let's do some experiment. Let's say we have 2 cross 3 matrix, right? That looks like this. 1 0 0 0 1 0 and 0 0 0, right? We can think of this example always. And x y z is equals to something 1 2 3, something like this, right? So in this, x and y are pivot variables. So what is the definition of z here, right? Okay, it has to be 0, right? It has to be 0 here. Hmm.
Just now what you have took in this to no free variables are there. If
Yeah, okay. Let me just check at least. Yeah, let me look
yeah,
from the
yeah.
book and then I can. Yeah, there's no free variables because yeah, again you are right. Then we are missing on the definition of free variables, I guess. Mhm. Okay, again, but okay, but if columns are full rank, again, then it goes to overdetermined case. So we can't get this scenario in an underdetermined case, but let's look off some overdetermined case, right? So it will be 3 cross 2. So three variables, two equations, right? So 1 0 0 0 1 0 and x y z, right? Yeah, is equals to let's look into this. 1 2 3 something, this into this, 1 2 0, right? Yeah. In this case, in the overdetermined case, right? In the overdetermined case, you have more variables than number of equations. So you won't get like you will always get invertible if the matrix A is square, right? Um, it will have at most one solution, right? But if it's not square, then it will be invertible. So it will have be a full rank matrix, and every column has a pivot variable. But if you have underdetermined, you won't get any case. If there are no free variables, the matrix will be the matrix. If there are no free variables, right, the matrix has to be square or it can't be underdetermined, right? If it has no free variables, it has to be a square matrix, or it has to be overdetermined system of equations. You can't have any underdetermined system of equations. And now if you have overdetermined system of equations with no free variables, the system can look like this. Is this clear, Satinder? So you can have this system, right? You have two variables, both are pivot variables, there are no free variables. And since it's a rectangular matrix, we can't comment on the invertibility. The inverse is only defined for square matrices, right? So but again, what is the number of pivot variables? Number of pivots equals to 2, which equals to minimum of rows or columns, right? Rows or columns, which is equals to 2, right? So it's a full rank matrix. So it will always be a full rank matrix. Valid conclusion. Ax equals to 0 has only trivial solution. That's not true. There can be other solutions, right? A is invertible. You can't comment because it can be over determined. So invertibility is not defined. And then every column has to be a pivot variable, right? Satyen, is this clear?
Yes, a little bit. Yes, still. Actually, when we are solving the question before during the lectures only, I had a doubt, so I thought I'll clear this part in like RREF when we are converting, for the equations.
Hmm.
So sometimes it is not guaranteed that we'll get the solutions or something like that.
Can you
But
give me an example for that? Because let's
at
do one
random,
thing.
we can take of any plane and try to solve by both by Gaussian and RREF. So that concept will be clear. At random,
So
can we take any plane three
no,
R three?
let's take lines, right? Let's stick to the 3D space and lines.
Like
Let's
like
start with lines.
suppose what is there sir, like what we have the syllabus, that part to different for the lines. So by just mere looking we can say that what will be the result. No need for going in the depth. Actually I think this concept is made for the enlarged dimensions, like
Okay.
for 10, 20, because actually when the examples is given for 2 or 3, so our thought is limited and we can't think beyond for that. I think so this system has been made for thinking beyond the 2 cross 2 and 3 cross 3, I think so, because we can come to know whether the solution is possible or not, because somewhere it must be implemented somewhere in technology or something like that.
Yeah, right. You're right. You're absolutely right. But what I'm saying is, whatever you are observing in the two dimension or three dimensions, it
Hmm.
essentially generalizes to higher dimensions also. So
Means
it's not
what
the
I'm
case.
no,
Huh.
there is a little bit doubt, like to understand the system, so it's okay. But
Hmm.
for 3D, but just by mere looking the equations, we can't say at once anything. 2D
Okay,
to
let's take some example, right? Let's take some examples and let's see.
yes.
So you are saying that let's take three equations, right?
Acha,
And
acha.
they are essentially planes, and you are trying to find the intersection of the planes, right?
At random we'll take any, and let's solve by Gauss elimination method, and that
So
this
do
one.
we want some properties like are the planes required to be parallel or something like that?
No, no, no. At random. Just now I'll give you some just I'm framing the question. Just give me 2 minutes, sir.
Yeah.
Uh, okay. One minute. Let's take one example. I've got number 3x
Okay.
minus
Can you type
3x.
in the chat box so that I there is no
It
confusion,
will.
right?
Uh,
Yeah. Okay. Let me solve this. Where's my teams? Teams, right? Hmm. I think let me share my screen again. Right. So the systems of equations that we are looking into is 3x minus y minus 2z is equals to 2. Then 2y, okay, 2y minus z is equals to minus 1. And then 3x minus 5y is equals to 3. Right. So let's look into this. Let's formulate our matrix. It is like 3 minus 1 minus 2, 0, 2 minus 1, 3 minus 5, 0. Right? This into x, y, z is equals to 2 minus 1 comma 3. Right? So how should I solve this? In the simple way? Hmm. So
Like
let
we are
me.
using that one RREF form. So
Okay.
let's try by RREF form.
So let's say we can say R3, replace R3 with R3 minus R1, right? Uh, o- okay, you will also need the augmented form, right? Let me put in the augmented form. So you get 3 minus 1 minus 2, 2 minus 1, 3 minus 5. Let's put in this. Oh, sorry. And then here you get 2 minus 1, 3, right? Now you say R3, replace it with R3 minus R1. You get 3 minus 1 minus 2, 0, 2 minus 1, 0, minus 4, 0, right? Oh, sorry, 2. And then 2 minus 1 or 3 minus 2 is 1, right? Again, what I want to say is R3, replace it with R3 plus R1. You get 3 minus 1 minus 2, 2, 0, 2 minus 1 minus 1, and 0, 0. R3 plus, right, minus 4. Okay, what was I was trying R3? Okay, I have done a mistake here. R3 minus 4 R1, right? Okay. Hmm. Okay, you can always take R2, right? You can always take R2. So R3 minus plus 2 R2, right? R3 plus 2 R2, you get 0, 0, or 2 plus 2 R2, 0, right? So you get 2 plus 2 R2, and then 1 minus 2 to minus 1 here, right? Then again, you would like to do is, right. Now you don't get a pivot, right? The algorithm exits here. You get no solution here, right? Hmm.
That only I had the doubt. Means ki, if you're not getting the pivot like in the row one in
Yeah.
any rows, so it means ki definitely there will be no solution. So
Hmm.
and one more condition that rank should be also less than the
So
order.
if
No.
you are not getting a pivot, this means it's rank deficient, right?
Okay. And it may be possible that we are not getting the pivot also, and rank is also not zero. That case will not come, no, sir.
Rank deficient. It's not about rank to be zero. It's about
No, no.
rank deficiency, right?
Rank will be same. Like we are not getting the pivot, and rank is also equal to the order. So in that case, so we'll get pivot. I think so.
No, look, there are two cases, right? One is full rank, right?
Hmm, hmm, hmm.
Full rank. Number two is rank deficient, right?
Okay.
So if you have full rank, you get a solution, right? There is a solution,
Okay.
right?
This only. Okay.
This you
And
agree with, right?
if rank deficient is there, then rank deficient plus we are not getting the pivots also. It means ki no solution.
If you are not getting pivots, this means it's rank deficient, first of all, right?
Okay.
If it's underdetermined system of equation, right? If it is
Hmm, hmm,
underdetermined, number of equations are what you say equal to more less than number of variables. Number of equations is less than number of variables, right?
hmm,
Or
hmm,
it is a square matrix. Number of equations is equals to number of variables, right?
hmm, hmm.
And you are not getting a pivot, then
Yes,
for
sir.
sure it's so in the first case, if it's the number of equations is less than number of variables, right?
Yes,
In
sir.
this case, the rank will can be full rank or not full rank. But if it's a square matrix and the it's rank deficient, you won't get a solution, right? Mm. Let me give you a simple example, very basic example. So let's say we have a solution z equals to 0, 0, 1, or a matrix look like x, y, z. Right? This is a rank deficient matrix, right? Then it says x equals to 0, y equals to 0. And yeah, what does this say? Hmm, right. So
Z,
now
Z
it,
can take any value.
now you when you look into this equation, this says x equals to 0, y equals to 0, and y equals to 1. Is this possible?
No, no, this is not
No,
possible.
right? And this is a rank deficient matrix, right?
Yes, sir.
Fine. So if it's rank deficient, you won't get the solution, right?
Rank deficient. We if it is rank deficient and pivots are one, then it may have I think infinite many solutions. That
Pivots are
condition, I think,
1.
if any one of the pivot is one, so it may have infinite many solution. I think so.
No, no, all the pivots are 1, right?
No, like we if we take two dimension, then it is a rank deficient as well as infinite many solution. If we see x plus y equal to 1 and x plus 2x plus 2y equal to 2, so that is rank deficient as well as this 2x equal to 2,
Mm-hmm.
2x plus 2y equal to 2.
Mm-hmm.
So here the rank deficient, but we are getting because pivot is 1.
Hmm.
If it so it means if you are not getting any at least one pivot, that
Hmm.
what you have I think explained before and only to get
Hmm.
the solution we
Hmm.
need at least one pivot.
Right.
You have only explained to
Hmm.
get the solution at least one pivot is necessary. Then only we can say either unique solution or infinite many solution.
Right.
So above case we are not getting at least any one of the pivot as one. Pivot means
Hmm.
one. I think so. So
Hmm.
that's why that in the above case no solution is there. What the
Right.
just example you wrote here, I think it may have infinite many solution.
No, there is a separation, right? First thing, if you have a rank deficient matrix, right, there are only two possibilities. It
Yes,
can
sir.
have infinite many solutions or no solution, right?
Mm-hmm.
If it's a full rank, you will have a solution, right?
Mm-hmm.
Now, if let's think geometrically, right? So when you talk about rank deficient matrix, this means either the lines or planes will be parallel or they will coincide, right?
Yes, sir.
So in the first case, you have zero solutions. In the second case, you have infinite many solutions. So these are the possibilities if the matrix is rank deficient, right?
Mm-hmm.
Is this clear? Right.
Yes,
For
sir.
the example that I showed here, right? This example,
Mm-hmm.
I was having this case, the parallel case, right?
Mm-hmm.
For the second example, you are showing this case, right? Coincident case, where infinite possible solutions are there,
Yes, sir. Yes, sir.
right? Now, when you do the pivoting, try to use Gaussian elimination for the first and the second matrix, right? For the first
Mm-hmm.
matrix, when you do the Gaussian elimination, you will get this 1, 0, 0, 0, 1, 0, 0, 0, 0, right? You will get this kind of setup.
Yes, sir.
For the second matrix, you will get this setup 1, 1, 0, 0, right?
Yes, sir.
In both the cases, you are getting pivots, right? None of the cases there where you are getting no pivot. Is this possible? Is this happening here?
Here in the here we are getting two pivots we are getting in the first case.
And in the second case, we are getting one pivot, right?
one pivot. So
Yet
that
in
is
the
the
first case, we are getting no solution, and in the second case, we are getting infinite many solutions, right?
yes, sir.
Right. So the number of pivots or getting a pivot doesn't essentially entirely tells you the story if you are getting zero or infinite many solutions. That's what I'm trying to say, right? You can
Okay.
have rank deficient matrix that can have zero or infinite number of solutions, but having if the pivot is to maximum number of pivots are reached for a square matrix, then you will have always have all fixed solution, one unique solution. If the number of pivots is less, then you can have zero or infinite solutions depending upon what is on the right hand side, right?
Okay, sir.
Depending upon whether the equations represent parallel planes, lines, or whatever hyperplanes, or coinciding parallel planes, coinciding lines, planes, or hyperplanes. So lines in the 2D dimension, planes in 3D, and hyperplanes in other higher dimensions. So it essentially generalizes well, but only these two cases basically arrive, right? So if you,
It means ki we are coming to the conclusion that ki having the pivot for rank deficient, it doesn't confirms that will have infinite many solution for the rank.
right, yeah, yeah.
So I thought ki just now we have done questions above. There it has been written ki to get the solution at least we want one pivot, something like that. It has been done earlier, just now in the explanation part above somewhere.
Which problem?
Somewhere we have done. I think in objective sum
Yeah,
is
this
there. Na?
one. You are told a system of
Yeah,
Amlineal
yeah, yeah.
equation and unknown.
At least one pivot here. It is written something like this.
At least one free variable, right?
Okay.
It has
Acha,
infinite many solutions, right? For infinite many
here,
solutions,
here,
you need to
here it
have
has
at
been
least
written
one
above
free.
also.
Yeah.
At least one pivot also. Here it is written. No, you have only written ki, equation should have at least one pivot, and I think you are right, sir. That part means ki if
Okay,
we are
okay,
getting
yeah,
at
yeah,
least
yeah. Okay, let me think. Okay, if you get so if you get no pivot, then it's a zero matrix, right?
uh, means ki
So
pivot
it looks
pivot is
it will
one leading coefficient should be one only, then only we can say it is pivot. If leading coefficient is not coming out to be one, then definitely it will have a no solution, I think so.
so it's a
So
zero matrix, right?
Mhm.
Now let's think of this, right? If I don't have at least one pivot, right?
Mhm.
Let's say if I have zero pivots, right?
Null
Then
matrix.
definitely RREF will look like this, right? You can see this zero matrix.
Yes, sir.
Does it have any solution?
So equation doesn't exist. It is a what I
Ah,
can think. It is an empty space. It
yeah,
is a
it doesn't exist essentially.
yes, sir.
So you won't get any solution here, right?
If nothing is there, so we can't talk about anything. I think so.
Yeah, you even can't discuss about what is the solution because it's not defined yet, right?
Maybe it is defined. What we can see that it is not visible to me. I can say like that. It is in some other word or something like that, which is not visible to us. That's why we are getting because whatever is visible to us, then only we can find in the matrix form somewhere.
But basically, it's the origin, right? Zero matrix is essentially representing the origin, right?
Origin, yeah, you're right, sir. So at origin,
Right.
we are not
So
getting. So at origin, so number of like line has not still started from there. We can see like that.
it's a point like I would say I will not like to comment on this, but it doesn't make sense if you're talking about zero matrix, right? And
Uh,
solution
uh,
to zero matrix, for
uh,
it doesn't make sense, right?
So you have means ki that only to get the solution you have only written over there ki at
Uh,
least one pivot is needed for this. So here though no pivot is there, so no solution. I can say that okay, we can't even think of this because we are not getting any single pivot also. A rank cannot be zero also for the matrix part. I think it is there that the minimum rank should be one. That is also there to solve. The minimum rank is one. I think
yeah,
so.
basically, if these things are zero, then the matrix is a zero matrix essentially, right?
Zero
And you
matrix.
can't do much with zero matrix. You can't
Yeah.
say anything. If you
Mhm.
multiply anything with a zero matrix, it will
No, no,
push
no, no.
down you to the origin, right?
Zero only.
So
That part.
so it's not a well-defined function also because multiple inputs giving the
No,
same solution.
no.
It's not one-to-one mapping, right? Matrices are essentially linear transformations, and yeah, they are linear transformations. And
Here,
then you are squishing everything to the zero. That's
no,
not
so I'm
something
not.
that we think of, right?
Here, just now in this question, what we have discussed, so that from this only, I have come to the conclusion that okay, to get the solution, at least one pivot should be needed in that, something like that.
I mean, for a matrix, for a non-zero matrix, there will always be at least one pivot for a any
That,
non-zero matrix, right?
so that one we are discussing. If we are not getting, then it may be no solution.
Though it will be a zero matrix, right? It will be a zero matrix. That's it.
No, no, I'm not saying ki, I'm saying ki the leading coefficient is not one for underdetermined rank. Then no solution will be there. We can.
No, let's say if I'm talking about this case, 0, 0, 0, 0 into xy equals to 0, 0, right? You have infinite many solutions, right?
Hmm.
Can you see this?
0, 0, 1. So I'm not getting for the 0, 0 part because no, 0, 0. Why we are taking this? I'm not getting because this is the we are talking
This
about
has
the.
zero pivots, right? Any other matrix will have at least one pivot. That's what I'm saying. If you're thinking of matrix with zero pivots, this is the matrix.
No, I'm not thinking of the zero pivot. Means I'm saying ki to get the solution, at least one pivot is needed. Means ki either infinite or many solution. That only can we come to the conclusion of that?
Yeah, it's by definition, if you have a non-zero matrix, it will have at least one pivot. And then if it has at least one pivot, then you can either have infinite many solutions or zero solutions. Now, if it is a full rank matrix, that is the number of pivots is equals to number of minimum of rows or columns, then you have a total solution, right? You have a unique solution,
Mm-hmm.
right?
Because just now what the example I've given, you have solved also. So in that
Hmm.
scenario also we can see that we are not getting any pivot. Just now what we you have solved just now. What I have example I've given, you have solved before that two
You
minutes.
are getting pivots, right? In the
No,
first case,
in that
you
one
are getting two
we are not,
pivots.
no solution we have got. Na, what the example I have given just now, and you have solved also, sir. So there you are getting no solution just now above to
We
this.
are getting no solution, but we have two pivots here, right?
Where? No, not in this case, sir.
Huh.
Before just now I have given the question. You have solved also.
This equation, right? This example,
And
right?
no, no, before this. No, no,
Acha,
not this.
just let me think. Let me see. Sorry. This case. Right.
So in
This
this
case, right?
case, it has no solution, and we are
Hmm.
not getting any pivot
Let me think.
because leading coefficient is 3 in the first one. It is not in the RRE form.
Now you can always scale a matrix row, right?
So it is not possible to scale it down. However, we'll do so, other will be disturbed. If we'll try to do, then it will be disturbed because I think it will be not reducible
No,
further.
you can always say, right? R1 equals to R1 by 3.
Okay, this we can say, right? So one pivot we are getting. So okay, so I was wrong only. Means ki you can get the pivot also, at least one pivot. So that also is not guarantee that you will get the solution only.
Yeah,
Getting
that's
at
what
least,
I'm saying. Hmm.
yes, this only example I was getting confused. Oh, I can divide by 3. You're right, sir.
So basically, there are three cases. Full
Hmm.
rank, which means
Unique
uh,
solution.
unique, which essentially means no. Let's not talk about no free variables, but you have pivots, right? You have some pivots, right? Pivots equals to rank,
Hmm.
right? Okay. Rank deficient, unique, right? Pivots equals to rank, and if it's square, right? If it's square, then you are getting
Requirement.
the unique, right?
Mhm.
So either zero or infinite solutions, right? Rank deficient, pivots less than the rank, right? Is this clear?
Yes, sir.
No, sorry, pivot is not less than the rank. Sorry. Pivots is less than number of variables.
Yes, sir.
Pivots is always rank. Number of pivot is always equals to number of is always equals to
Right.
rank, but it will be less than number of variables. That's the case. That's it.
Hmm.
Fine. I think this is clear, right?
Hmm.
Again, you have if you have any pending doubts, you can ask me in the next session also.
Okay, sir. Thank you, sir. Thank you for time, sir. Okay. Good
Okay.
night, sir.
Good
Good
night.
night, sir. Thank you, sir.
Okay. Thank you.